Hey everybody, let's talk about the standard deviation. So what is a standard deviation? In a nutshell, it's the average distance of each data point from the mean of the data set. It represents the overall spread of data in a sample. Now, this is important because the spread of the data is representative of the amount of variability in your sample. It also helps you standardize or compare between two normal distributions. It's often the starting point for measuring variability in your sample, and that's critical to statistical hypothesis testing. So, calculating standard deviations and understanding what they are and how they work are really important if you're going to go very far in statistics. All right, so how does this work? It all starts with normal distributions. And normal distributions have a secret. Let me just make a few normal distributions here. Let's see. Normal distributions. Let's see. There we go. I better switch songs or I'll get copyright infringement. Okay. So here I've created a few normal distributions, and you'll notice that there's something similar about all these distributions. In fact, that's why we call it the normal distribution. It's because they all have something in common. And the secret that normal distributions have is that there's only one normal distribution. And in order to describe that one normal distribution, you need two pieces of information. First thing you need to know is where is the middle of this distribution? So you can slide this distribution to the left and to the right and move the middle around. And then the other thing you can do is you can either stretch it out or you can squish it together in the middle. And those are the only two parameters that you need to worry about with a normal distribution. You know where the middle is. We measure that by taking the mean. And then we need to look at how stretched out or how spread out the data is. And you do that using the standard deviation. Okay, so think about what an average is. An average tells you, it's a way of summarizing the values in a data set. So it summarizes where along that bottom axis each of the data points lie, as it summarizes them as a group. Now, if only there was some way we could summarize how spread out the data are. And that's what the standard deviation tries to do by calculating not just the average, but the average distance of each data point relative to the mean. In other words, on average, where is the data? That's the mean. And then the standard deviation asks how far on average is each of these data points from that mean. So I put it to you that the standard deviation is really just a fancy average. Okay, so let's look at the formula for an average first. I'm going to walk you through this. And in order to create the formula for the average, we're going to add up our numbers and then divide by the number of items that we have. Okay, so I'm going to just take this text and I'm going to convert it into a formula. So the first thing I'm going to do is I'm going to put this formula up here. Essentially what I'm saying is add them up. All right, let's take that first part. You're going to add up your numbers. Well, we have a symbol, sigma, that means sum. And them is your data set, X. So we're going to add up all the data in data set X. So add them up, sigma X. Then we're going to divide by the number of items that we have, or n. We'll symbolize that with n. So we come up with this formula that's sigma x over n. So this is just a way of taking what we know about the procedure for calculating a mean and turning it into a simpler or shorter language. We're simplifying it by using these symbols to represent it. Okay, now I want to show you I'm a little hesitant to do this, but I want to show you the formula for the standard deviation. Don't get intimidated by it because we're going to break it down and we're going to see how it works. Okay, so this is the standard deviation formula. And I want to point out to you that there are a couple of elements that are familiar to you now from the previous formula. We have adding, something about x is up, although we've kind of done something different here. Right? And we have an n down here. So you can maybe connect some of the elements of the formula for the average to the formula for the standard deviation. Okay, so let's walk through. I'm going to help you see exactly how these two are related. And let's go back to our formula. So we've got add them up and divide by the number of items. Okay, so we can try this with a data set. So if we do this, we can I created a data set X here. And I put in some values, just a short data set, 3, 1, 2, and 2. So those are our, let's say we have 4 participants in an experiment, and we ask them to rate on a scale from 1 to 5 how happy they are. And we want to find out how happy is our group of participants. And so they rated themselves a 3, which is pretty good, 1, 2, and 2. So if we wanted to summarize that, we could calculate the average. Okay, so first thing we do, we add them up, add up the x's. So 3 plus 1 is 4, 5, 6, 7, 8. Right? So we have 8 is the sum of x. And the number of items is 1, 2, 3, 4. So we need 8 over 4. And if you simplify that, you get 2. So our average is 2. Okay, now the question is, how spread out are these data? How spread out are these data? Well, one interesting way we might go about this is we might say, well, maybe we can summarize, now that we have the mean, we can summarize how far away each of these data points is from that mean. So if our mean is 2, then we could say, well, the 3 is 1 away, 2 is 0 away, it's on the mean, and so on and so forth. And maybe we could calculate the average distance from the mean. So how would we do that? Well, maybe we take our formula for the average, but instead of sigma x, we just say sigma of each data point minus the mean. After all, distance, or the difference between each x and the mean, should give us something along these lines. So that would give us a formula that looks sort of like this. So I want to try this and see if it works. So we have sigma x, so that's each data point, minus the mean of the data, and then we divide by n. Right? So that's just average distance from the mean. Right? So distance from the mean. All we've added is this minus x bar, the distance from the mean. So what happens if we do that? Let's calculate it out. Okay, so first I took my data set, 3, 1, 2, 2, same as before. And now each data point, I said, I'm going to take this data point minus the mean, and I'm going to get some number. Right? So 3 minus 2 is 1, 1 minus 2 is -1, 2 minus 2 is 0, 2 minus 2 is 0. And so now I have my distances from the mean. And if I add them up, I get 1 plus -1 is 0 plus 0 plus 0. So that's all 0. And then I've got my n hasn't changed, it's still 4. So now this would be 0 over 4. Right? And then if I calculate that out, I get a 0. Okay, does that make sense? Does it make sense that there's 0 spread of the data? Zero spread of the data would mean that they're all exactly the same, right? But obviously, they're not all exactly the same. Some are 3, some are 1, some are 2. So that doesn't make any sense. So I must have gone wrong somewhere. Where is the problem? Well, notice that I have negative numbers here that are counteracting the positive numbers. So think about a normal distribution. It's symmetrical. There's going to be roughly the same amount of data above the mean as there will be below the mean. And so if you do it this way, it's always going to cancel out, and you're going to get 0. So what do we do about this? Okay, think about it. We're talking about distances here. And think about when you drive to the grocery store. When you drive to the grocery store, think about how many miles away it is. For me, I drive to a grocery store that's about 4 miles away. Now, when I drive home from the grocery store, how many miles do I travel? It's not negative 4 miles. If you look at my odometer, it goes up, not down, by another 4 miles. So here's the problem. Distances should always be positive. I've got negative numbers in here. Those don't make sense because I'm talking about how far away it is from the mean. I need a distance, which is positive. Okay, so how can I take care of this problem? What could you do? What if you took this, what if you squared the numbers? If you square a number, then if you square a positive number, it's positive. If you square a negative number, it's a negative times a negative, so it becomes positive. So you'll wind up with all positive numbers. But of course, then they'll be sort of distorted because you multiplied them together. Well, what do you do to fix that? Well, what if you took the square root? So why don't we add to our formula here, why don't we, instead of x minus x bar, why don't we do x minus x bar squared so that all those distances become positive? And then to get rid of all the squaring, once we've added everything up, let's take the square root. Right, so what does this look like? Now we have the square root of the sum of x minus x bar, the distance from the mean, squared, divided by n. Right? So again, we've got, it's just an average, sum of something divided by the number of items, but the thing we're adding up together is the distance of each data point from the mean. And so we don't get negative numbers in there, we square it, and then because it's squared and we don't want to have it squared, we take the square root. With me so far? We're just building upon this formula to make it work for an average distance from the mean. So let's calculate that. So let's try this now and see if it works. So if we do, I have here our data set. I have the thing we had before, which is x minus x bar. So we had 1, -1, 0, and 0. Okay, now we're adding this next column here. Now we're doing that x minus x bar squared. All right, so I did 1 squared, which is 1. -1 squared is 1. 0 squared is 0. And 0 squared is 0. Okay, now we're getting somewhere. Now I can add these up, right? So if I add up this column, because we got to remember, we got a sigma, we got to add 1 plus 1 plus 0 plus 0. That gives us 2, right? 2. And we then have to, our n hasn't changed, it's still 4. So 2 over 4 gives us 0.5. Now we have to take the square root of 0.5, which gives us this kind of wacky number, 0.707, or we can round to 0.71. But now we have a summary of the average distance of each point from the mean. And that's all there is to it. So I hope you can see that there are some elements from that original formula for the mean, and we just fancied it up in order to make it an average distance from the mean. Okay, some of you are bursting at the seams looking at this formula because you're saying, yeah, but what about that missing piece on the bottom? Right? N minus 1. What's that business all about? Okay, well, let me walk you through this. But first, let me say, if you are measuring your entire population of interest, then this is the formula you need. This is all you need to do. Sum of square root of the sum of x minus x bar squared divided by n. But there's a problem. If, on the other hand, you are measuring a sample and trying to estimate your population based on that sample, that brings a level of uncertainty into the mix. Right? Because what are the chances that my sample exactly represents my population? Probably pretty low. So because of that, I need to make some corrections because of the assumptions that I made about how closely my sample represents my population. So let me walk you through sort of how this works. When we calculated the average, we used only numbers that we got from our sample. We didn't have to do any kind of transformation to the numbers in order to calculate our average. However, anything that's wrong with that average is going to contribute problems to anything else we do to that data down the line. So when we calculated our standard deviation, remember, we didn't just use the data from the sample, but we also used data, we used the average in the formula. So now anything that's wrong with our data is going to be compounded by the fact that we have that average included in there as well. And so we need to do something to fix that. So let me show you how this works. And the way I like to think about it is I like to travel back to my childhood. And I think about playing Ninja Turtles on the playground. Now you can use any, maybe you like Power Rangers, just depends. But any group that has a fixed number of individuals in it will work for this. So let me show you. So here I have the Ninja Turtles. We're going to go out and we're going to play, and I get together with my friends, and we're going to be the Ninja Turtles. Right? So let me ask you, who is this person going to choose? Do you know? Who is this person going to choose? This person. You don't know. You can't peg who this individual is going to be. They could choose freely any one of the Ninja Turtles. Right? So you can't predict with any certainty which one this is going to be. And so it could be anybody. Well, let's say my friend comes along and he says he claims Raphael. That's his favorite turtle, so he claims Raphael first. Okay, now let's move on to the next one. Who is this person going to be? Can you predict with any accuracy who this person is going to be? It could be any of the remaining 3 turtles. You just don't know. So this one is free to choose as well. So let's say he chooses Leo because he likes the swords. Right? Okay. Now I'm thinking I better choose quickly because I'm going to lose out if I don't choose. And I really don't. I wanted to be Leo, but Leo's taken. So I go to my favorite because he was always the kind of geeky tech scientist kind of guy. I go with Donatello. Right? But I was free to choose. You wouldn't have been able to predict that I was going to choose Donatello. I could have chosen Michelangelo as well. All right. Now, Ralph, the 4th friend, what's he going to choose? Does he have any choice? You know, what's he going to do? He's going to say, I'm going to be Leonardo as well. No, it's not going to work. We're all going to gang up on him and be like, you can't be Leonardo. He called it already. All right, so he doesn't have any choice but to be Michelangelo, whether he likes it or not. And so the key element was that some of us had choice and others didn't. Right? And the reason this works is because we said from the outset what we knew the outcome was going to be. We knew we were going to have these 4 turtles. And so while this one was able to choose, this one can choose, this one didn't have a choice. And it didn't matter which one, who chose what. The last person to pick didn't have a choice. If we were going to have this outcome, that was the choice that had to be made. Right? In other words, they lost some freedom. They lost freedom of choice. How many individuals lost the ability to choose? Well, 1 less than the number of people we have, or n minus 1. 3 of the 4 got to choose. The last one, right, didn't. Now, if you did Power Rangers, you might have 5 or 6 of these, but it works the same way. Even though there's 5, when you're free to choose. When you get to the last one, n, if there's 5, minus 1, 4 of them were able to choose, but 1 of them, we lost 1 degree of freedom. Okay, with me so far? Now let's move on to numbers. Okay, so in our standard deviation formula, we provided a mean. And we said the mean was going to be 2. Okay? And the rest of, when we went back into our data set, those other things were free to vary. But we said that our population mean is 2. So what's this first number going to be? Well, it could be anything. It could be 100, it could be 7, it could be -2, right? And these numbers could be anything conceivably. But what were our actual numbers? Well, if I start plugging them in, 3, 1, 2, what is this next number going to be? Well, if we know the outcome is 2, then there's no choice in what this number could be. In other words, this number is not free to vary. These numbers could have been anything, but once you get to that last one, if the outcome is going to be 2, that number's fate is determined already. So how many of these were free to vary? N minus 1. N minus 1. Okay, so this one has to be 2. So in order to correct for this problem, because we're estimating from a sample to a population, and we're saying we think we know what that mean is going to be in the formula, instead of dividing by n, we're going to divide by n minus 1. And so that leaves us with our final version of the formula. The square root of the sum of the distance of each data point from the mean squared over the degrees of freedom, or the sample size, minus 1. And there we have it. So let's plug this into our formula. So here's the formula again. And if you do the math, now all we've done from the first time we did it is we've changed, instead of n, we're dividing by n minus 1. So instead of 4, that's what n was before, now it's the square root of 2 over 3, right? Which gives us a slightly different number down here. We get the square root of 0.06 or 0.67. And if you do the math on that, use your calculator, you get 0.816 as our sample standard deviation. So when we go to our normal distribution, we say it has a mean of 2, and it has a standard deviation of 0.816. Now, the cool thing about these kinds of things is that there are a number of properties that normal distributions have that makes this measurement actually quite useful. And the main thing is because all of the data fits under that curve somewhere, and that normal distributions are the same across different situations, no matter where you slide them to or how far you stretch them out, we know certain things if we know that standard deviation. These properties of normal distributions and how spread out the data are allow us to do some really cool things. Soon I'm going to be making some videos about z-scores and about probability, and really this becomes the engine for much of the inferential statistics that have guided scientific thinking for many, many years. Okay, so that I hope has been a basic introduction to a standard deviation and how to calculate it, where the formula comes from. And I encourage you to make up some data sets and go to town trying to calculate standard deviations. A little practice of these steps where you go through and step by step walk through the formula and kind of start with your data set, move on to x minus x bar, then square it, then add them up, right? So that gives us this number. And then divide by n minus 1, then take the square root of the whole thing, and you get your standard deviation. A little practice goes a long way. All right, I'm going to wrap it up on this topic, and I will have more videos on statistics real soon. See you next time.